Okay, good afternoon everybody. So the last time, if you recall, that we stopped at analyzing some definition of the stability and also the main key theorem which help us to compute the nominal internal stability, and we also see one example that it's not only the closed loop from the input to output you need to analyze. So it is not only the map which you need to see for the stability analysis from the input to output, but you also need to see other maps from the disturbances or from all the external variables. So in these examples, if you recall that the map from input to output, that is to say from the set point, was stable, but the map from the disturbance to the output was not stable. So in that case, we cannot say that our closed loop system is stable. We saw this kind of polynomial in the last lecture, or let's recall very quickly. We have seen this polynomial, okay, which is in terms of s. Basically, this is a generic way of writing that polynomial of nth order polynomial where all these coefficients ai are constants, belongs to the real number. So here the problem to be studied deals with the question of whether that polynomial has any root with non-negative real part. So this is what we analyze. If the root has a negative real part, then it is stable. If it is not, then it might be marginal stable or could be unstable. So here we would see a generic case of nth order polynomial. We know that if this question can be answered by computing the n roots of the PS of this polynomial. So if you recall very quickly, when we see, or in that paper which we considered in the very first slide, in that paper only this kind of equation was solved up to third order system, okay, but now we have this kind of high computing tool which can of course solve this kind of equation for the nth polynomial. But the only idea is not only to solve the equation and find that where the roots are being placed in the S plane. In many applications, there is also an interplay between the value of this coefficients and the location of the roots. So we will see now how these the coefficients and the location of the roots will going to play. So there are some couple of definitions before we start our algorithm. Polynomials having all their roots in the closed left plane, that is with non-positive real parts, are known as Hurwitz polynomials. Okay, and if we restrict the roots to have negative real parts, we then say that the polynomial is strictly Hurwitz. So if there is a root only on the imaginary axis, we understood the last time that it would be marginally stable system. Okay, in that case we cannot say it is strictly Hurwitz, but it's a Hurwitz. So let's see some properties for this polynomial. So here you see that the coefficients a to the power n minus 1, that is this coefficient, it satisfies this mathematical relationship, and these lambda I or all are the roots of the PS, that is the polynomial. Okay, so there is one relationship between the coefficients and the roots. So if you notice, if you pay a close attention, assume that all these roots, okay, all these roots lie in the left half plane of the S plane. Okay, so all these values will be negative. When they would sum up, with the negative sign, this value will become positive. Okay, just note this point that this a with subscript n minus 1 is a positive. Okay, the coefficient a naught, the last coefficient a naught, satisfied this property, this mathematical relationship, where again this lambda I are the roots of the P of S. Depending on the order of the polynomial, this would be either negative or positive. I hope you are pretty much clear about the mathematical notations, where this big sigma denotes the summation and this big pi denotes the product. So basically this is the product of all the roots of the P of S. Property 3 reads, if all roots of PS have negative real parts, it is necessary that AI, that is to say all the coefficients of this polynomial, okay, so this is just a necessary condition, not the sufficient one, right? And necessary means what? Though there might be possible that all the coefficients are positive, in that case the roots of PS might not be having a real negative real parts. Okay, do you see? So it only says if the root has negative real parts, then it is necessary that all ai should be positive. Okay, not the other way around. Okay, just pay a bit more attention on this property 3, which is again, recall this thing what we have just said. So this is, since this is a necessary condition, even if you see, so what we are really trying to compute here, the stability of such kind of polynomials. And we know from the theorem that if the roots are on the left half plane, okay, the system with this denominator would be a stable system. Okay, so you cannot give your final judgment looking at this condition only. Okay, I hope this thing is clear to you now. Now the property 4 reads, if any of the polynomial coefficients is non-positive, if any of the polynomial coefficients is non-positive, either negative or 0, meaning to say that these coefficients could either be negative or 0, then one or more of the roots have non-negative real parts. And saying that the roots have non-negative real parts, it might be a marginal stable system or it could be an unstable system. So you can say straightforwardly, if there is a negative sign or negative non-positive coefficients, then that system is not stable. Okay, then we need to see whether it's a marginal stable system or an unstable system. So now there is a Routh algorithm which determine whether or not a polynomial is strictly Hurwitz. Okay, so now we're going to see this algorithm. So that polynomial could be written in this way, in the short notation, where p of s is the summation of ai into s to the power I, where I is varying from 0 to n. So basically it is a nth order polynomial. So this is how we compute the Routh array, where we first write this column with seeing all the power of s, then we start filling this table, this one, okay, by using this formula. Okay, we will see, maybe this appears might quite complex, but when we start seeing the example, you could see that how this kind of table is constructed using this formula. Okay, so consider a polynomial p of s and its associated array, meaning to say this one, this associated array. Then the number of roots with real part greater than 0 is equal to the number of sign changes in the first column of the array. So what it says, so the first step is to construct this Routh table. Okay, and then we just see only this first column, and what we see in this first column, the number of sign changes, so the number of roots with real part greater than 0 is generally equal to the number of sign changes in this first column. Okay, let's consider this example. So here we have this polynomial which reads s to the power 4 plus s cube plus 3s square plus 2s plus 1. Now you can see that all the coefficients are positive, so it is necessary that it's okay, it just satisfies the necessary condition. So now we need to inspect whether or not this is a Hurwitz polynomial. So how we construct this Routh array? So we start with the very leading order of this s to the power 4 cube square s to the power 1 or s to the power 0, and then in the first row, in this first row of s to the power 4, we write the alternative coefficients, that is to say this one, 1, 3 and 1. In the second row, that is s cube starting with 1, 2, and that's it. Now the rest of the rows which are remaining to compute using the formula is this one, s square, which is compared by 1 into 3 minus 2 into 1 divided by this one, which gives me 1. Similarly for this one, 1 into 1, here you can assume 0. Okay, 1 minus 0 divided by 1, it gives me 1. Okay, similarly we proceed further to write the complete this table. So now you see, only in the first column there are no sign changes. There are no sign changes. All the coefficients remain, all the values remain positive, meaning to say that none of the roots lie on the right half plane. Okay, something not clear? What is not clear, sir? Okay, so let's recall this thing. Okay, I hope I can. Okay, so generally let's see once again that how we write this table. We have this s to the power 4, okay, this polynomial. So we write the polynomials in the decreasing order. Okay, 4 3 2 1 0. Now we need to write the rows corresponding to this orders of this S. So we start with the S to the power 4 coefficient with alternative coefficients of the order of the following order of the system. So 1 3 1. Okay, for S cube we start with this one 1 2, and we don't have another coefficient, so we assume it's 0 for the moment so that we can compute this next row using that formula we saw the last time in the last slide. And this formula reads, I need to multiply this into this minus this into this divide by 1. Okay, 3 minus 2 divided by 1 gives me 1. So now if I need to write this one, I take this row, this column. Okay, since there is no number, so that's why I assume it's 0. 1 into 1 minus 0 into 1 divide by 1 gives me 1. Okay, now I don't have this 0 because this was an assumption, right? So now see only this one. So 1 into 2 minus 1 into 1 divided by 1 gives me 1. Okay, I don't need to write this one because I don't have any values here. So similarly, to write this one, I assume once again to 0. 1 into 1 minus 1 into 0 divided by 1 gives me 1. Okay. So this is how we construct the table, and then when after looking at the table, basically looking at the sign changes in the first column, we say that whether the system is a Hurwitz polynomial or the system is stable or not. Okay, so this says the system or this polynomial is a strictly Hurwitz polynomial because there is no sign changes. The system will definitely be a stable system, no marginally, no unstable. Okay. Now next, see this example where this polynomial reads this one, this PS. Okay, so now with the leading order, I start with my first column, S to the power 5 4 3, basically this is 2 1 and 0. Okay, so you should read this as 2. So with respect to S to the power 5, I have what, 1 12 and 3, right? With respect to S to the power 4, I have 5 13 and 6. So now I need to compute the rest of the rows. So I follow the same, I use the same formula to come in the same way to write all these values, right? So once you have this table, now again we see the sign changes in this first column, and here we see that there is a sign change from here to here. So this is one sign change from plus to minus, and there's another sign change from minus to plus, which says that there are two roots which lies on the right half plane. So this PS is not a Hurwitz polynomial, and this would be an unstable system. So whenever you see a minus sign here and the rest of the sign are positive, meaning to say that there's two sign changes from plus to minus and from minus to plus. Clear? So this is how you can use this Routh array to compute the absolute stability. Okay, just pay this attention now that why I introduced this term absolute. Okay, so there are a number of cases also which you need to take care of while writing this table. What it says, the case 1, we first consider the case when the first element in the row associated with S to the power n minus k is 0, but there is at least one other term which is non-zero. Meaning to say, let's consider if I have this kind of polynomial. Okay, here you see none of the coefficient is missing. Okay, starting from S to the power 5, I have the decreasing order of the S. So I write this. So when I write this Routh array, and while computing, I see that there is an element 0. So if there's a 0 in this first column, okay, you cannot proceed further, because what it say, if you use the same formula, 0 into 6 minus 2 into 3 divided by 0, okay, this would be an NaN, this would be not a number, so you cannot proceed further to test whether the system is stable or not. So the remedy for this kind of issues is, so what do? We substitute this 0 Okay, we substitute this 0 with the positive epsilon. Okay, why? First we saw that what is the sign of this value. If it is positive, okay, we replace it with positive epsilon, where epsilon is a itself is a positive quantity. Okay, or let's say the minus or the plus of mod epsilon. If it is minus, then we replace it with minus mod of epsilon. Okay, this is what it says. So once we replace this with epsilon, since here we have the positive sign, so that's why it's a positive epsilon. Okay, we write this positive epsilon, and then further we compute the fill the rest of the element in this array. Now we have all the elements, and then we start computing the limits for the rest of the elements in the first column only, because we are concerned only with the first column, right? So what do we see here? What do we see here? So if there we have this 6 minus 6 over epsilon, and if epsilon is a very small value, if epsilon is a very small value, then this number would be very big, meaning to say the negative of the number is very big. We have a positive 6, so this element will be a negative element in this first column. Okay, now let's see the second one. If I put epsilon to the epsilon is very close to 0, okay, this number, okay, basically this number to epsilon would be a very less number, and I am subtracting it from 1, so this would be positive, right? On the numerator I have the mod epsilon square, so this would be a positive if epsilon is a very small number, meaning to say this element would be a positive number whenever epsilon will tends to 0. Okay, so we saw that, okay, this number would be positive, very small value of positive, this is negative, here we have the positive, and the next one is also positive. So how many sign changes? From positive to negative, negative to positive, 2 sign changes. That is to say, 2 roots of this polynomial will lie on the right hand side of the S-plane. Now case 2, where the case 2 reads, it's not only the first element but the entire row. If it is 0, then what do you do? Meaning to say, this kind of situation where there is again no coefficient is missing, or yeah, no coefficient is missing in the decreasing order of the S, but I have such kind of situation where I cannot put the epsilon further. So how do you deal with this situation? So what do you do? Let's see this example once again. So you go one row above, that is to say this one, and then writes a polynomial with respect to this row, and this, for this one, it will, the leading order of the S would be 4, and it would be alternating as well, meaning to say for this one I will have S to the power 4 plus S square plus 3. Okay, the order of the S is also alternative, right? Then I divide this whole polynomial with this PA polynomial, which is basically this one. Okay, then again I have this polynomial, this one. Okay, so once you divide this polynomial by this polynomial, the residual is this one. Okay, you can check, you can apply the Routh array on this polynomial as well, because why? Because when you put P of S is equal to 0, here when you put P of S is equal to 0, that is to say that PA is equal to 0 and this polynomial is also equal to 0. Either of this polynomial could be 0. Then you can apply the Routh array on this table to see further if it is of higher order, whether there are any roots in this polynomial which are lying on the right hand side. But this is clearly visible in this PA once you compute the roots, that there are roots of this PA which are located on the right hand side. The real part of the root of PA is positive, says that this polynomial, the system having this polynomial in its denominator is an unstable system. So now the usability, here what we are testing basically the absolute stability. Now once we will talk about the marginal stability, there we the relative stability, sorry, then we introduce the difference between why I introduced that term absolute stability, because here the polynomial is given to C and I'm just checking whether this polynomial is Hurwitz or not. And what does it say? There are some roots of this polynomial, right? Once you solve this equation, okay, there would be some roots, okay. Now you know the exact location of the roots, that where the roots are located in the S plane, and based on that you say that whether the system is stable or not. The interesting point would be that if you have a knowledge, or if you have this kind of knowledge, that by moving any root, how the stability will going to affect. Do you see the difference? Here we are checking just the stability. Whenever the this polynomial is given to us, we see that, okay, whether this is Hurwitz or not. Absolutely, okay. The interesting point would be, if there is some parameter in this polynomial, how I can see the stability of the system with respect to that variable. Okay, so let's see this one example, effect of parameter variation. So let's say we have a feedback control loop given by, this is the forward path G naught C. Here we assume this simple feedback loop. Okay, here we have this G naught, here we have this C, and this is basically the forward path only, the multiplication of G naught and C. So the G naught of C is given by this transfer function, and here we have one parameter K, and this K of course is coming from the controller only, right? So again I write the closed loop, that is to say 1 plus G naught C, and this polynomial is given by this PS. And here you see now that there is variable K which is coming from the controller. So again, using the route array, you can construct this table starting from S cube, S square, S1, S0, and the rest of the element in the column. So now for the stability, what do you need? That all the element in this first column should be positive, meaning to say that 1 minus 0.5 K should be positive, this condition, and K itself should also be positive, right? In that case, all the elements in the first column are positive. So once I compute the inequalities on K, I come up with this condition that the value of K should lie between 0 to 2. Okay, it is straightforward. That what condition I have, 1 minus 0.5 K, I have this 1 minus 0.5 K which should be greater than 0, and I have another condition which is K greater than 0, which it would read that 1 should be greater than 0.5 K. So K should be less than 2 and K should be greater than 0, basically. So we have this relationship. Okay, if the value of K lie within this region, then and then only the system would be stable, right? So here in fact, while there is an interesting point here, while determining the stability of the system, you actually computed the controller that could give you a stable closed loop. Okay, determining the stability is one step, constructing the controller is another step, but within the one step only you have analyzed the stability and you have constructed the controller. If I say that we generally design the controller whenever we have the desired specifications, here the desired specification what I imposed is the stability, that's it. Okay, I impose that my closed loop should only be stable. So for what values of C or for what value of K which is inside this controller would give me a stable closed loop. Okay, so only the stability is the main desired specification for this closed loop. So the relative stability analysis, so this is what I was talking about, that here in the last one we actually constructed the controller. Okay, we determine that with respect to the value of K, how the stability will going to affect, first thing. Now another interesting thing, if I want to know with respect to the location of the pole itself, that if there is a pole of, so say what I am trying to say, so let's say we have okay, I will write here, if I have the C of platform to write, okay, so if I have the C of S, okay, now I know that my K is fixed. Let's suppose I know the K, the gain, the steady state gain I know. Okay, let's say I know this one. Now my controller is something s plus a and s plus b. Okay. Now once I write that polynomial, okay, in terms of KAB, okay, I would be having a polynomial, right? Once I write the closed loop 1 plus G into C, this would give, okay, the next page. So what I'm trying to say, we have this 1 plus GC, the numerator of this gives me the P of S, okay, the numerator of this gives me the P of S, and I have a controller which is of this structure, for example, right? And among, now here there are three constants K, A and B. Assume that I know you know these constants and only this constant is unknown. Okay. Once you write this polynomial P of S, you would be having this S plus B somewhere as one of the coefficients. Okay. In fact, as because this is a root also. Okay. Somehow this will appear. Okay. So with respect to the, so basically this is this scenario. You are in the S plane with the sigma and j omega. You have a number of roots. Okay. R1, a complex conjugate of this R1, R2 and two complex conjugate R3. Okay, there are three roots. So what do you do if you want to analyze the relative stability with respect to, let's say, R1? So what do? You shift the axis from this to this by doing this. This variable, the change in variable, what do you say? S is equal to Z minus sigma, basically this axis. So you shift the axis only, okay? You shift the axis with respect to that pole. So now your new polynomial would be in terms of, Z, okay? Now again, you form a route array with respect to the variable Z, and there you can see that how many roots are lying on the right hand side of this point. Okay, it does not speak about the stability. Okay. That is to say that if it says there are two roots, on the right hand side of this axis, what does it says? It is to this right. Okay, this is this region where the system is stable. This region is stable, but this is unstable. Okay, the main axis would going to remain the same. It's just the relative with respect to only this axis. You see, okay, how many roots are lying on the right hand side, right? So because as we have seen, if any root is lying on the left hand side, it is pretty much clear that the system is stable. Okay, but there are other design specifications as well, okay, which we call the transient specification, where it is required to know the location, the state or the performance of the system with respect to the location of the roots. So before computing the other specification, the stability is the first and foremost. We check with respect to the roots how the stability would going to affect, okay, how the stability would going to affect. Then later on we take into account other design specifications, which are basically the transients one, okay, the settling time, the, so here we will consider one design problem. Okay, what it says that we have a large welding robots which are used in the today's auto plants. The welding head is moved to different positions on the auto body and a rapid accurate response is required. So now you can imagine the situation where we have the welding robots, let's say, which are located on the top, and here they weld. Okay, there could be a batch process, okay, where they weld the different body parts. Okay, and we need to have a closed loop such that, so let's say if I give the position, okay, I have this thing, move this side, it should move in a very quick time and it should be stable, no vibration or nothing, or no some weird behavior to reach to this path. Okay, so this is that kind of situation. So the block diagram of a welding head position system is shown below, where the head dynamics is given by a third order system. Okay, now you need to determine the range of K and A for which the system is stable. Now my controller is of this form, and so this is my G of S and this is my C of S, right? So now you need to find the range of K and A for which this overall system is stable. Just the stability is the performance specification here, forgetting about all the other specifications. So I think there was some glitch here in the audio video. So where were we? We were here for the design problem. So this head dynamics is given to you, and the controller is also given to you, and they form a closed loop where you give the desired position. Okay, like I was saying, you give a desired position. Okay, so that the data head position should follow this desired position. Okay, that is why we form the closed loop, right? We had the head dynamics, we build the controller, we give the desired position or the tracking, so that it can, so whatever be the head position is, can track the desired position. So now you are asked to determine the range of k and a for which the system is stable. Okay, so we'll take a couple of minutes break. So in the meantime, you try to solve this problem and give me the range of k and a. In the meantime, if there are any questions, I can take. So there's one question from RCPITMH. Is route criteria applicable for non-linear system? I haven't seen so far, and in fact, if you see, okay, so first you need to see. So I think the answer to your question would be in your question itself. So we started building this route array, or we started using this route algorithm, assuming that we have such kind of polynomial. Okay, and this polynomial is nothing but a denominator of the transfer function. So meaning to say, whenever we speak about the transfer function, it is implicit that we are considering only the linear systems. The Laplace, yes, Laplace can be applied to any function. I'm trying to recall if there's, okay, we'll take this question in the break. So in the meantime, try to solve this this problem. Okay, I guess some of you were able to solve the question. RCPITMH.
Good afternoon, sir. My question is, how can we predict about marginally stable system by using route criteria?
How you can predict? Basically, you cannot predict, you can only compute, right? So from the route criteria, how can you do the marginal system? So let's go back to the definition. Okay, so that once you compute the using the route array, so let's say if the whole polynomial is given to me with all the coefficients, I just need to see whether it is Hurwitz or not. So what we generally do, we just see the first column, the number of sign changes, and then based on the sign changes, we say that the system is stable or unstable. Okay, for the marginally stable, the one of the root has to be on the imaginary axis, purely on the imaginary axis. So there we need to compute the roots. Yes, DCRU, Rotash.
Yes, sir. Very good afternoon, sir. Hello.
Yes.
बोलो बोलो. Hello.
Yes.
Hello. Getting me, sir? Hello.
Yes, I can hear you. Ask your question.
Yes, please. Sir, we can say the transfer function of a circuit is valid for the transient time.
Say it again.
Sir, can I question?
Say it again.
Sir, for any circuit, is the transfer function in the transient time valid, or we can say, can we calculate a transfer function for a transient time for any circuit?
For a transient time.
Yes, sir.
Okay, well, in what context? Because this is a very, I would say, when you speak about the transients, it is generally you describe the transients by the impulse functions. Okay.
Okay, sir.
If
Yes,
there
sir.
are sudden changes and the impulse function itself does not have a proper representation of its own. You see, yes, first of all, what do we do once we define a transfer function? Basically, it is for the entire dynamics from time t is equal to 0 to infinity, which also includes some smooth transients at time t is equal to 0 when you start applying your input to the closed loop.
Okay, sir. At last, the conclusion is that we can calculate the transfer function for a given circuit in the transient time.
In the transient time, I won't say perfectly yes. but it needs to analyze at what kind of transients you want to visualize or you want to represent, let's say. Okay,
So, sir,
if it is a
it would.
transients, if these are transients which you want to realize that start at t is equal to 0 whenever you apply a step or an impulse input, okay, those you can represent.
Yes, sir.
But the
Got you, sir.
transients which appear due to switching within the electrical circuits, okay, these are, I would say, you need to analyze it further.
Okay, sir. Thank you very much, sir.
Okay, the question was, is route criteria, no, can we find out stability of multiple routes on imaginary axis using route? Okay, so if you know that there are multiple routes on the imaginary axis, if there are multiple routes on the imaginary axis only, then system is very close to an instability. Okay, in fact, even if you have an integrator, which amounts to say that you have one route on the imaginary axis, in that case also we say that the system is marginally stable. But if we have multiple routes, meaning to say the nth order integrators within the system, then it is very close to instability, because for determining the stability using route array, you just need a polynomial. Okay, so once you have a polynomial with all the assumptions or the criteria, then once you start building the route table, it would be fairly visible that whether the system would be Hurwitz or not, or the polynomial. Okay, so we'll take some couple of interactions later on. What was the Were you able to solve the design problem which I gave to you? Okay, so the problem was, we have the g of s 1 upon s plus s plus 2 s plus 3. We have the c of s k s plus a on s plus 1. Okay, so we proceed in the same way, where we write the 1 plus g into c, which is basically this a s plus a over s s plus 1 s plus 2 plus 3. Okay, and from here I would have my polynomial, which I need to analyze whether it would be Hurwitz or not, and basically it is the numerator of this equation. So it would be your s plus 1 okay. I need to determine the stability or the Hurwitzness of this polynomial. So let's simplify this one. This would read s to the 4 once you simplify it. Okay, so this is your characteristic equation or the polynomial. Okay, so let's construct the route array from that polynomial. So we'll write the first column in terms of s. So this element will read 1 11 6a 6 k plus 6. So let's write this element which we need to compute b3. This would be ka, right? basically this is AA. So 111 AA, and this will read the second row 6k plus 6. So I need to compute this element B3. This element would be straightforward. 6 into k plus into Ka divided by 6 would give me Ka. So this would be B3 into k plus 6 minus 6 into k plus a Ka divided by B3. Let's write this element as C3, and this would be nothing, and this would be the last one Ka. Okay, and this B3, let's write this separately. B3 would be what? Would be 66 minus k minus 6 will give me 60 minus k by 6. Your C3 would be B3 k plus 6 minus 6 Ka divided by B3. Okay, for the stability we need that all these elements in the first column should be positive. That is to say B3, C3 and Ka all should be positive. Okay, so if I say B3 should be positive, meaning to which will give me, so let's see, first B3 should be positive. This would give me 60 minus k by 6 should be greater than 0, equivalent to k should be less than 60. Now let's compute the C3. C3 also says C3 should also be greater than equal to 0, which reads k minus 60. If you see your last equation, k minus 60, k plus 6 plus 36 Ka, which should be less than equal to 0. Okay, after simplifying this one, it gives me A should be less than equal to 60 minus k plus 6 and 36k. Okay, so I have this condition which says that k should be less than 60 and A should be less than equal to this function, which is a function of k. So now suppose if you put k is equal to 40, what you will get? Once you put this 40, you will get A should be less than equal to 0.639. Okay, and the multiplication of this should also be positive. That is to say k and A should be positive. So you see k and A should also be positive. So in fact here you have three conditions. One which says with clearly gives you the condition on k, which straight away give you the condition on k. Yes. So once you start increasing the value, what would happen? So you will soon realize that there are some limiting factors which would implied by the third condition of this element, that this element Ka should be greater than equal to 0. Okay, and this condition is a very serious condition also, which you need to realize, because if K and A are both negatives, okay, this will at least satisfy this condition, and this will satisfy this condition also, which is say that K should be less than 60. So you need to see what is happening to A. So you need to compute here if K is negative. So this is how you can compute, in fact design your controllers by taking into account the stability criteria only. Move on to the next topic, which speaks about the root locus. Okay, we can also determine the stability by plotting the root locus in the S plane. So basically this is another tool which also gives me the stability of equations of this type, which is of course is the characteristic equation. So the root locus approach can be used to examine the location of the roots of the characteristic polynomial as one parameter is varied. Okay, so here in this root locus, with respect to only one parameter, I can see that how the stability of the system is being changed. So this basically gives me the relative stability analysis. So we do the same procedure. Assume that the nominal plant model is given by G0 and that of the controller is this, where K is unknown to me and CA is almost known to me. In fact, it is known to me. Then the closed loop poles are the roots of this equation, right? And this is the denominator of the closed loop transfer function. So whatever the roots I am going to get for this one would be the closed loop poles. The set of all points in the complex plane which satisfy the above equation for some positive value of k is known as the root locus. So we'll see this point, that what do we mean by the root locus and how do we draw it and how it can help us to determine the stability. So let's see the general framework. We have the polynomial which is represented in this way: 1 plus lambda f of s is equal to 0, where lambda is an unknown parameter and fs is a known transfer function which is represented in this way: the ratio of m over d, and the order of the ms is we put this small m, and for the denominator we put the small n. So now the solution to the root locus problem requires us to find the set of all points in the complex plane which are solutions for the above equations for all non-negative values of lambda, right? We would be plotting this in the S plane, and whatever be the points would lie. So you see, we are basically plotting this equation in the S plane. So all the, and this is equal to 0, it is an equation, okay, which you need to solve for different value of S, for different value of lambda, right? So if you know a lambda, you would going to get some roots, some S, the value of S in the complex plane. So all these values which satisfy these plots in the S plane is basically the root locus. So there are some building rules for the root locus. We will see one by one, and also we see that how we use this plot, these points to plot basically the root locus. So what it says, the number of roots in the last equation is this one: 1 plus lambda f of s is equal to 0. The number of roots in the last equation is equal to the maximum of m comma n. Okay, m is the degree of the numerator polynomial and n is the degree of the denominator polynomial. Thus the root locus has maximum of m comma n branches. Okay, the first point. So this is the observation, that observe that S naught belongs to the root locus for lambda greater than or equal to 0 if and only if it satisfies this one. Okay, we will see this point once we start plotting this. And observe this point also, that if S naught belong to the root locus, so whatever the plot we are going to get on the S plane, the corresponding value of lambda is lambda naught, where lambda is naught is given by minus 1 over fs naught, basically this one. So these are the observation for observing point. Now the next point says, rule says, a point S naught on the real axis, that is S naught which belongs to the real number, is a part of the root locus for lambda greater than 0 if and only if it is located on the left of an odd number of poles and zeros. Okay, so first in the S plane, what we do, we write the location of poles and zeros. Okay, and then we see that how, with respect to this rule, we draw a line or a plot basically. Okay, now the fifth rule says, when lambda is close to 0, this lambda and the last equation, then n of the roots are located at the poles of f of s. When lambda close to infinity, then m of these roots are located at the 0 of f of s. Okay, so possibly you have all these, I suppose you must be having these slides with you. So I would recommend that if you take these rule book in your hand, okay, which constitute this 9 points, so we straightforwardly can go that how you can plot directly using this this rule book, let's say. Okay, what it says, we have a plant with a transfer function g naught and a feedback controller with transfer function c of s, where g naught is given by this one and cs is given by this one, and we want to know how the location of the closed loop poles change for alpha moving in positive real numbers. So how do we do it? First we notice that the closed loop poles are the roots right? I just write 1 plus GC. 1 plus GC. On simplifying, this gives me this polynomial, which is basically the characteristic equation. Now I can write this equation in my general framework, that is to say 1 plus lambda for fs, where this lambda is unknown and here alpha is unknown. So I can transform this equation in this form to apply those rules. So after dividing this whole function by this one, it gives me lambda is equal to 4 alpha and f of s is this one. So now the rule 1, what it says, that the number of roots is equal to the maximum of m comma n. Here I have m0 and I have 3. So there would be 3 branches. Thus the root locus has maximum of m comma n branches. So it says that 3 branches would be there. Okay. Point number 2 and 3 were the observation. So you can observe them once you have a root locus with you. The point number 4 says a point S0 on the real axis, that is S0 belongs to R, is part of the root locus if and only if it is located to the left of an odd number of poles and zeros. So you compute the poles and zero of this transfer functions. Okay. Quickly you notice that there is a pole on the imaginary axis and there is no pole on the right hand side of the S-plane. So there is one pole lie on the imaginary x on the origin, basically on the origin. So origin is 1. So from there the whole real axis would be a part of your root locus, because whatever the roots you are going to get from this equation, they would complex conjugates. Okay. So there is only one root which lie on the real axis, and that is why it says the negative real axis belongs to the locus, because you have only one odd number of poles. Okay. Rule 5 says when lambda is close to 0, then n of the roots are located at the poles of f of s, that is at p1 up to pn, and if n is greater than m, which is not the condition, so we leave out the statement which says for alpha close to 0, amount to say that lambda will close to 0. Okay, the roots are at the poles of f of s. Okay, so here you quickly see that I have a pole at 0 at the origin, and I have other 2 poles which are the complex conjugate. So one is this, and if I add them 2, I would have 3 odd number of poles. Okay, that is why it says the negative real axis belongs to the locus. The rule 6, it does not apply here also. Rule 7 says that if n is greater than m, which is the situation here, and lambda tends to infinity, amounts to say that alpha would tend to infinity in another way, then n minus m roots asymptotically tends to infinity, meaning to say 3 roots will tend to infinity following asymptotes which intersect at sigma comma 0, where sigma is being computed by the formula given in the rule number 7. So basically this formula roots sigma is equal to the summation of all the poles, what it says, minus summation of all zeros of the f of s divided by n minus m. So here you can see that we do not have any zeros. What we have, only the poles. Okay, we add these poles. Once we add this poles, divide by 3 will give me sigma is equal to 1 minus 3, which is basically an asymptote. And the angle of this asymptote you can compute by the formula also, which is given in rule number 7, which is given by eta k is equal to 2k minus 1 into pi divided by n minus 1. So from there you get this 3 different asymptotes angles, varying for k is equal to 1 up to n minus m. So in principle you would get 3 asymptotes, 3 angles for these asymptotes. The rule 8 does not apply here also, because it applies if n is less than m. Now the rule number 9 says when the root locus crosses the imaginary axis, okay, say at s is equal to plus minus j omega c, then omega c can be computed either using the Raut-Hurwitz algorithm, right, using the same way if there is any zero occurring there, or using the fact that s square plus omega c square divides exactly the polynomial, this ds plus lambda of ms, for some positive real value of lambda. So if so the rule number 9 reads, if I have the characteristic polynomial which is given by this one, when two of the branches crosses the imaginary axis, then this polynomial can be exactly divided by this one, s square plus omega c, leading to a coefficient equal to s plus 1 with a polynomial residue equal to this one. And if we make the residue equal to 0, we obtain omega c and this lambda c, where it will going to cross the imaginary axis. So after putting all these rules together, we have this root locus, which reads, I have one pole at the origin, I have two complex conjugate poles. Okay, now the branch will start from the odd number of poles. So here I don't have any roots, from here I have roots, so whole this imaginary axis belongs to the root locus. Okay. It always starts from the zeros. Okay, so it start in this direction, it start from this root in this direction, following these 1, 2 and 3 asymptotes. Okay, right, these are the 3 asymptotes. Let's see this once again. Okay, first see all the 3 asymptotes. I don't know if I can select the different color. Okay, good. So first see the 3 different asymptotes, one this one this one, and one is this one. Now see the root locus. The root locus start from the poles. So I have one pole here, I have one pole here, the complex conjugate poles. So the whole real axis will belong to the root locus because there are no roots lying on the real axis. So I have odd number of roots on the right hand side. Another will go in this direction and another one will go into this direction following these asymptotes. And the point at which it crosses this imaginary axis are given by this one, omega c and lambda c. Okay, so what do you see here? So once you have the plot, how you can analyze? So this branch, what you see here, until the point you are on the left hand side, your system is stable. Okay, so this part, if you choose the value of alpha in such a way that you are falling into this region, okay, because this is a part of the root locus and when it is lying on the right hand side, so there are heavy chances that system can go unstable system. So you see what you realize of all that you construct, first of all you analyze the stability, you construct the controller, and you also find out the range, that for what values of this alpha, which is a part of the controller or the pole, it also how the stability is changing. If you fall into this region, okay, your system is unstable. If you strictly stay at this point, okay, you are marginal stable. If you choose the value of alpha in such a way that you are always on the left hand side, then the system is stable. Okay, so you are checking the absolute plus the relative stability as well with respect to the unknown parameters, in fact unknown parameter. Okay, so there are some other refinements also which you can see in your lecture notes or the slides which are given to you. Okay, there are different refinements of drawing the root locus, and basically you can design your controllers taking into account the stability criteria and the transient performance specifications as well, right? Because yeah, okay, we'll stop this discussion here for the root locus. Okay, so we'll take the last topic for today, which says about the stability in state space. So first of all, we will see what we have been talking about the states in the earlier lecture also. So what do we mean by the state? First of all, so we know that to determine a system response at any instant t, we need to know the system's input during its entire past from minus infinity to t. So what it says, so let's say if I know the input, let's say, okay, if I have this closed loop system or the system which is u and y, the input and output, okay, I can, and we have seen the transfer functions which are basically represented as the ratio of y and u. Okay, if I at this current point, if I know the u, then only I can compute the y. Okay, to compute the future values of y, I need to know the future values of u. Okay, In fact, even if I want to know the past value of y, I need to know the past values of u. Okay, but this variable, the state variable, gives me the flexibility that if I know the value of this state variable at that particular time, that then I have the knowledge of the entire history. Okay, this is the beauty of the state variable which it captures. So state basically is a memory of the system. So if you are here at time t naught, okay, at time t naught you know the value of what is the value, what is the value of state, then you know what would have been the value for the t less than t naught. And if you have the value at t is equal to t naught, then those values are known as the initial state. So it says the state variables, which are generally denoted by this xi of t, are the minimum number of variables of a system such that their initial values at any instant t naught are sufficient to determine the behavior of the system for all time t greater than t naught when the input to the system is known for t greater than equal to t naught. Okay. So x is a this state is a very important variable and a significant variable for analyzing the system, whether it would be linear system or non-linear system. So how do we determine the stability? Say, let's suppose, so far what we have considered a single transfer function which maps only one input and one output. Okay, if you have a number of inputs and number of outputs, then instead of having only one transfer function, we would have a matrix or transfer function. Okay, we would have a matrix of transfer function, and then to determine the stability of that multi-input multi-output system, we need to see all the transfer functions if they are stable. First of all, we need to see the forward path transfer function, then we also need to see all the sensitivity functions as well. So now you see how many transfer functions we need to realize to finally say that okay, our system is a stable system, if there is a case of multi-input and multi-output system. But if we have a representation of a system in such a way, okay, this is a very generic representation of what we call the state variable representation. So what we did for the nth order differential equation, okay, for the nth order differential equation, if we take if we convert it into the transfer function form, we would have a transfer function which would be of order n as well. Okay, but this representation gives us flexibility that we can represent the nth order differential equation into a single first order matrix differential equation. Okay, and this is just only one representation, do not bind to it only. Okay, there are number of ways to represent the state variable representation as well. Okay, so this is how it is represented. X dot is equal to ax of t plus b of t, where a, b, c, d are the matrices of appropriate dimension, and they are just the constant matrices. Okay, if we are concerned about the linear systems, and here we have the variable x, which is generally the state variable, the input variable u, and the output variable y. Okay, so now the question arises, okay, if you try to think by yourself, consider this system y, and because this is a very important and thinkable question. If you have a y here, okay, in the system, you have a u here as an input to the system, you have the accessibility, okay, you have the accessibility to measure these two signals. Okay, whatever you are giving to the plant, you can measure, whatever is coming out of the plant, you can measure. Okay, but when I say that state is an internal variable, okay, state is an internal variable, it is here somewhere. Okay, how can you measure it? How can you measure it? So for the moment, assume that you have a representation in such a way, and you have an assumption also that this x is measurable, right? Because this question must have appeared from the way that time only when I say that x is an internal variable. Okay, it was not written here, that x is an internal variable here, so somewhere it is within the system. How do you measure it? Assume that you have the measurement of this x. Okay, so now we have all these matrices. So in fact, even if we have the system representation in this form, the state representation form, we can transform this system equation, and once we have the characteristic equation, we can use all the tools, right? We saw the route array, we saw the root locus, right? So it says how we can convert, how can we use this stability analysis on the characteristic equation. And note that it says for the unforced system, right? So let's write our state equation, which reads x dot is equal to ax plus bu. When I say the unforced system, unforced system means that I'm putting u is equal to 0. That is to say, whatever the system, this an unforced system is also called the autonomous system, which depends only on the initial conditions of x, right? So I represent x dot is equal to a of x, ax. Now I know that since I'm considering the and this is a constant matrix, the solution of x is generally solution of x is generally have the exponential behavior. Okay, so I can assume that let x of t is equal to k e to the power lambda t, where it is for every element of this x, right? And this lambda I are basically the roots. Okay, we also call them the eigenvalues. Okay, for the moment, just if you haven't heard about this eigenvalues, right? So just note this down that these lambdas I are also called eigenvalues. Okay, so okay, so xit is equal to this one. So this is an element. Why I call it I in a subscript? Because this is one of the element in this vector of this vector x dot. Okay, we need to say my x is basically x1 up to xn, right? There could be, it is a, okay. So if I go to the next page, how can I write what we assume that xt now in a vector form is k e to the power lambda t. So if I put this into my equation, what I considered x dot is equal to ax would give me lambda k, that is the differential, taking the differentiation of this one xt with respect to time t, e to the power lambda t is equal to a k e to the power lambda t, right? Or this exponential would cancel out. Did I miss something? Okay, so basically this one is your x, right? Lambda x is equal to this one is your also x, lambda x equal to x, and finally what you could write lambda I, where I is an identity matrix of the same order of this A. So 0, right? Now you have the polynomial, or you have the polynomial which will be represented in this way. And now above this equation, basically this equation will have a non-trivial solution if and only if you have satisfied this condition lambda I minus a is equal to 0. These are basically the set of equations. Okay, this would set of equalities which would have a non-trivial solution if your system of equations satisfy this equation. And this is nothing but a polynomial, right? So how this polynomial come into the picture, we could see by considering a case study. So suppose we have a we consider this case study of inverted pendulum, where we have this cart, the moving cart, which of capital M, we have with a rigid rod attached to it, a ball. Okay, so this is a very basic case study which you might have played in your childhood as well, by putting a bat on your hand and just controlling it. So basically this is the same one. This cart moves in such a way that this pendulum stays straight away. Okay, so what we have assumed here, so that this capital M is much greater than small m, and the angle of rotation, this theta, is very small. Why I make this assumption? Because from the very beginning I could have the linear equations. Okay, and since we are considering only the linear system in the state space, it would help us to analyze the stability as well. Okay, so this theta, basically this angle of rotation, is very small. So this this ball stays very close to the theta is equal to 0 position, around this position. So you can write this basic equation from the mechanics of this board, from this mechanics of this problem. We have the sum of forces in the horizontal direction for both the masses. Okay, sum of torques about this axis, about the pivot point. Okay, we come up with this equation. And now, so basically these two equations are required to write the dynamics of the whole system. So like I said, how do you measure the states? The question what arises. So it's you, the designer, okay, who has the full flexibility to choose the states, right? So you choose the states which you really want to control. So I choose my states y theta, theta, and theta dot as the 4 state variables. Okay, I choose these 4 variables, and once I taking use of these 4 variables and taking use of these two equations, I wrote this four first order differential equations, right? And from that I could build, once I put into a vector form or the matrix form, this will give me this A matrix and B matrix. Is it very quick for you to visualize that from these 4 differential equation how I can come up to this A and B matrices? Because let's say if you write all these 4 differential equations, x1 dot something, x2 dot, x3 dot, x4 dot, okay, then you could write a single x as x1, x2, x3, x4 as an A matrices with 4 different elements. Would be a matrix of 4 by 4, be x1, x2, x3, x4. I know that I have only one single variable u, one input variable u, so it would be a 1 column matrix u with 4 elements. Okay, so in this element, this would be the x1 dot. You see, this is the x1 dot. This x1 dot is equal to the multiplication of these 3 constant element with respect with this state variables plus constant u. So in this equation, if you see that x1 dot is equal to x2, so I would have only 1 here, the rest would be 0. Similarly, what it says that x2 dot is only x3 and ut, so x1 x2 would be 0. With respect to x3, I have minus mg by m. With x4 also is 0, and with u it's 1 by m, right? If you notice, x dot 3 is equal to x4, that all this element 0, 1, 2, 3 and x3 dot is equal to x4, and it is also 0. If you see the last equation, x dot 4 is x3 and ut, so this is 0, this is 0, x is what, g by l, this is 0, and this could be minus 1 over ml. So from there I got my A and B matrices. Now once I have this A, B matrices, how can I determine the stability? Let's see. So while taking this A, B, C, D matrices, okay, what I need to write, that the determinant of lambda I minus a should be equal to 0. What it reads, okay, I is an identity matrix. So in the last page we saw that the order of the a was 4 by 4. Okay, so I identity matrix would be of 4 by 4, and when I say I is 4 by 4, it is represented by the one having in the diagonal elements. This is my identity matrix. So if I put this I and a from the last page to here, this would give me the determinant of lambda minus 1 0 0 0 lambda n g by n 0 okay. So once I compute the determinant of this matrix, this gives me, this is a square bracket, not a matrix anymore. Right, this is, you see, my nothing but the characteristic equation. What it says that, let's go in this direction, that lambda square minus g by L is equal to 0. That there are two poles, two roots on the 0, on the origin, at the origin, and I have two other roots which are at plus minus under root g by L. Amount to say that my system is unstable, which I know from the physical perspective also, which we realized, which we saw yesterday also, that if I put this ball at theta is equal to 0, this is an unstable point. Theta is equal to pi. It's an unstable point, so it will fall down. Okay, and this analysis shows me, yes, why it will fall down, because of this. Okay, so this is what we have for today. From tomorrow, from the next time, we will see the frequency response and the stability in the frequency domain. So let's take some couple of questions now and some interactions if requires. So the question says, what is the important role of root locus in stability? Okay, I suppose this question must have been answered when we discussed the usability of the root locus, that it gives me the, I could analyze the relative stability with respect to the unknown parameters. Either it could be a pole or it could be a constant in the controller. So it says BMSC, what is the exact difference between root locus and Routh-Hurwitz? I suppose RH you mean by Routh-Hurwitz, or either relative humidity, I don't know. So okay, so if it is root locus and Routh-Hurwitz, the difference, it generally, like we saw, that if you want to see some relationship between the coefficients, okay, and the stability, then there your Routh-Hurwitz come into the picture. Okay, because there it gives you the knowledge on, in fact, some relationship between the coefficients and the stability. Okay, on the root locus you can see the relative stability with respect to only one parameter. Okay, this is another difference. Like in the Routh-Hurwitz, when we built the Routh-Hurwitz table, there were two unknowns, k and a. Okay, and we find out the range for two variables at the same time during that Routh array, that okay, what would be the range. But in the root locus we can vary on, we have to fix one parameter, and then we vary if there are two parameters, of course, then we need to find the relative stability with respect to another parameters. Okay, so you can vary only one parameter at a time in the root locus. Okay, and while in the Routh-Hurwitz you can have the ranges on the variable at the same time, right? Okay,